When we were talking about the Apollo missions to the moon, we said 6 of them landed. So Apollo 11 landed Sea of Tranquility, and Apollo 12 landed, and that was really sort of the end of the test sort of missions and into the fully operational ones after that. Apollo 13 didn't land, but 14, 15, 16, and 17 landed. So 6 of them landed in 6 different spots on the moon. And the spots were selected to give some scientific understanding of the nature of the moon. But really, remember, you're only getting a snapshot. How well would you understand Earth if you just picked 6 spots and looked at Earth and measured Earth at those 6 spots? Would that really give you a full understanding of Earth? Probably not. And so that's why the missions to the moon, the Apollo missions, were a really good start. But we needed more. And that's why we're trying to go back and study the moon more. Apollo 11 landed in the Sea of Tranquility, Mare Tranquillitatis, and when they set up the seismographs, they found layers and layers of basalts. Now, it's not just one big thick layer of basalt in the seas here. So it's not just one big thick layer, but really multiple layers with fragmented ground underneath. And that would suggest that it was not just the impact formed the sea and then lava quickly filled it in. That the volcanic eruptions happened sequentially. A volcanic eruption that flooded the area with molten rock, was then solidified. Then another volcanic eruption flooded it with molten rock, which solidified. Then another volcanic eruption, and so forth. So building it up layer by layer. Apollo 12 landed in Oceanus Procellarum, and it was right near a ray of a crater that it was streaking across. So it would pick up some rocks that would actually came from a different part of the moon. And it was also right near where Surveyor 3 had previously landed and done studies looking, in one spot. But this way we were able to bring back rocks. And so this was a geologically interesting place. And one of the things they found was that underneath Oceanus Procellarum, that yes, there were layers of basalt that made up the sea, but those layers were on top of what we call megaregolith. The megaregolith there was big, chunky blocks of material blown out by a later impact, by an earlier impact. So what does that mean? Well, it means that we got this big impact that created the impact basin, and then another impact happened and tossed stuff into it before all the basalts had come and laid on top. Okay, so the basalts from volcanic eruptions. So this is again telling us a story about what was happening on the moon, saying that these basalt flows happened that made the seas, but there were like multiple impacts in a fairly short period of time before any of the basalts got a chance to flow. Likewise, when we looked at Apollo 14, that was again near the Framaro Formation along the edge of Oceanus Procellarum, the Framaro Formation itself, which is big piles of megaregolith up here. So stuff thrown up by impacts, and the basalts were in layers over here. Apollo 15 landed along the edge of Mare Imbrium, a place called Hadley Rill. Remember, a rill is like a lava channel. And right near the Apennine Mountains. The Apennine Mountains are basically the edge of the giant impact that made Mare Imbrium. And what they found was that, again, just like with the Apollo 12 mission, that we have megaregolith with basalts on top. Again, suggesting that there was a sequence of events that happened here that involved several big impacts before you could get the lava, the basalt flow on top. Apollo 17 landed in the Taurus Littrow Valley, right along the edge of the Sea of Serenity. And again, we got basalts in there. And then Apollo 16 was the only one that landed in the lunar highlands, right near the Descartes crater. And it found basically just lots and lots of large regolith, stuff thrown out by multiple impacts from all over the place. And so that was the geological findings from Apollo. The Maria were basically flow basalts. The ground underneath was fragmented. You had regolith and then megaregolith from other giant impacts. One of the things they found from the geological studies, the seismic results, was the moon has a much, much thicker crust than Earth does. Percentage-wise, it's vastly thicker, but actual number-wise, it's thicker. The moon's crust is thicker than Earth's crust, and the moon has a very thick mantle. In fact, the mantle goes almost all the way down to the center of the planet. There's a very small core, so the moon is primarily mantle material and then crust material with a very, very tiny core. Percentage-wise, the core is a tiny portion of the moon. The upper part of the upper part of the lunar mantle has been solidified. The moon's much smaller than the Earth, so it's cooled off and frozen solid. So that makes it lithosphere. The lithosphere makes up most of the mantle. Only the lowermost part of the mantle is still in that plastic or fluid sort of state where it can move around. That's where most of the moonquakes come from. So the moonquakes are normally not caused by tectonic activity like on Earth, but by flexing of the moon as it moves around its orbit around the Earth. It's sometimes at perigee, sometimes at apogee, and so the difference in distance is changing the gravitational pull and the tidal forces which are flexing the moon a little bit. The crust itself is vastly thicker than Earth's crust. Now, that's even in the thinnest places, the moon's crust is as thick as the Earth's thickest crust. And so that suggests to us that percentage-wise, the moon's made of different stuff than Earth. And so that's an oddity. The other thing that we found was that the crust was actually thicker on the far side of the moon from the orbital studies that we made than, so on the back side of the moon, the thrust seemed to be thicker than on the near side. Okay, now how do we do that? Because we only landed on the near side with the Apollo missions, and that's the only place we put seismographs down. Well, as the mission was landing on the moon, the other part of the mission, remember the mothership, the command module kept orbiting. And as it orbited the moon, where the ground was more dense, gravity caused the spacecraft to speed up a tiny bit, and where it was less dense, it slowed down a little bit. And so by measuring that, they could measure what they call mass cons, or mass concentrations on the moon. And from that, they were able to figure out a density profile. And that gave them the realization that the crust tended to be a little bit thicker on the far side than on the near side. So that means when you got really big impacts on the near side, you would crack enough here that the cracks would penetrate down enough for lava to come up from the mantle. On the far side, these impacts didn't quite penetrate down far enough. And so that's why you don't have as much mantle material working its way through on the far side. So that's why the far side of the moon has very few seas compared to the near side. The most recent lunar interior findings from some of the orbiting spacecraft we've got there is that the core is incredibly small, probably no more than about 300 or so kilometers in diameter, about 330 kilometers in diameter. That's less than 1% of the moon's volume. So over 99% of the moon is mantle and crust. So the core is this tiny little thing in there. And the density of the core, as near as we can tell, is much lower than the density of Earth's core. So it's probably only about 5 grams per cubic centimeter. Well, that's actually lower density than we expect for an iron core. That suggests that possibly the core is contaminated with sulfur extensively. Well, on Earth, there's not as much sulfur in the core. A lot of the sulfur is in the mantle, and so again, this tells us a little bit about the composition of the moon. It's got the same stuff that Earth has. It's just in different proportions than Earth has. Some of it is very similar, but again, the proportions are slightly different. The moon is much more like Earth's crust and mantle than it is the overall cross section of Earth. So the percentages of things are different. The seismographs they were left behind by the Apollo astronauts, did detect moonquakes. They were expecting to have some kind of quakes, because that's what we have on Earth. That's how we figure out what's going on inside the Earth. This tectonic activity creates seismic waves going through Earth. Well, there are no plate tectonics on the moon, so that means the seismic waves are tiny. So there was very little in the way of moonquakes. So the main source of moonquakes was believed to be tidal variations as the moon orbits the Earth. The other thing is impacts. In fact, in later missions they had artificial moonquakes they created that as part of the mission, they caused the third stage of the Saturn V to plow into the moon as a big impact. And then after the astronauts had left the surface of the moon in the ascent stage of the lander, then once they had transferred into the command module in orbit, they would plow the descent stage back into the moon, slamming into the surface, creating a small impact. Other meteorite impacts also produced occasional moonquakes. But the man-made impacts were one way of creating seismic waves because there weren't very many seismic waves that were naturally generated on the surface of the moon.